Have you ever stopped to think about how your computer is pulling off its daily magic trick? I mean, you're on a video call, your email is syncing in the background, and you're browsing a website, all at the same time, through one single internet connection? How does all that data not just crash into each other and become a complete mess? Well, it all comes down to two very different, very important digital messengers working behind the scenes. So here's the game plan. We're going to start by looking at that digital traffic jam. Then we'll meet our two main characters, TCP, the reliable one, and UDP, the fast one. We'll put them head-to-head to see their strengths and weaknesses, and finally, we'll check out the secret address book that keeps this whole system running smoothly.
All right, let's dive right in. To really get this, we first need to appreciate the huge problem our computers are constantly solving every single second they're online.
Okay, just picture this. You've got data packets for your video call, chunks of that email you're downloading, and pieces of the website you're loading all streaming towards your computer at the same time. They're all funneling into one single connection. So how on earth does your computer know which data goes to Zoom, which goes to your email client, and which goes to your web browser? It needs a sorting system like a digital mailroom to deliver everything to the right place.
And that system starts right here, with something called a port number. Think of your computer's IP address as the street address of a giant apartment building. That gets the mail to the building, but the port number, that's the specific apartment number. It makes sure that web traffic gets delivered to the browser's mailbox on, say, apartment 443, and not to your video game's mailbox next door. It's absolutely crucial.
So, now that we know how data finds the right mailbox, we need to talk about the delivery service itself. And first up is TCP. This is the premium white glove courier service you hire when every single piece of the message has to arrive perfectly intact and in the right order. No exceptions. You see, TCP is what we call connection-oriented. It doesn't just start throwing data into the void. Nope, it's more formal than that. Think of it like making a phone call. You dial, the other person picks up, you both say hello, and only then do you start the actual conversation. TCP needs to establish that formal connection first.
And here's the really clever part. TCP is, well, it's meticulous. Once that connection is open, it chops up the data, numbers every single piece, and sends them off. The computer on the other end is checking them off a list. Got packet 1, got packet 2, wait a minute, I'm missing packet 3. It then sends a message back saying, hey, can you resend number 3? This way, it guarantees that the entire message is put back together perfectly, every single time.
That initial phone call I mentioned, it has a name, the three-way handshake. And it's as simple as it sounds. Your computer, the client, sends a message, a SYN packet, saying, hey, you there? I'd like to connect. The server replies with a SYN/ACK, which means, yep, I'm here and I'm ready for you. Then your computer sends one last ACK message saying, awesome, connection established, here comes the data. It's this polite little dance that makes the whole thing so reliable.
And check this out. This isn't just a diagram from a textbook. This is a real-life screenshot from a tool called Wireshark that listens to network traffic. And you can see it right there, clear as day. A SYN/ACK, and an ACK. That's the proof. That polite conversation is happening millions of times a day, all over the world, in just milliseconds. So, where is this level of perfection needed? Well, think about loading a secure web page, like your bank's website. You need every single piece of that site to load correctly. If even one packet is missing, the whole page could break. Or worse, the security could be compromised. For things like that, reliability is absolutely king. All right, so that's TCP, the reliable courier. Now let's meet our second messenger, UDP, who has a completely different philosophy when it comes to delivering information. UDP is basically the polar opposite of TCP. It's connectionless. There's no handshake, no how do you do, no formal setup. It just wraps the data into a packet, slaps an address on it, and sends it out as fast as it possibly can. For UDP, the #1 priority is speed, not reliability. This is what we call a fire and forget system. Because UDP skips all the polite handshakes, the packet numbering, and the acknowledgments that make TCP so robust, it's way lighter and way faster. But here's the trade-off, and it's a big one. There's absolutely no guarantee that the packets will arrive at all, or if they do, that they'll be in the right order. And again, if you look at a network capture, the difference is just striking. Look what's missing. There's no SYN/ACK dance. The computer just blasts out a request, in this case asking for an IP address, and gets an offer back. It's so much more direct, and because of that, it's incredibly quick.
So you're probably thinking, why would I ever want that? Well, think about a live video call or streaming a football game.
If one tiny little packet of video data gets lost, what happens? You might see a single pixelated block for a split second. A tiny glitch. Isn't that so much better than the entire video freezing for a few seconds while slow, methodical TCP stops everything to re-request that one lost packet? For anything happening in real time, speed is king.
So there you have it. We've got a reliable courier TCP and our speedy messenger UDP. Let's put them side by side and really nail down the crucial differences.
This table really says it all, doesn't it? On one side, you have TCP, formal, guaranteed, but a bit slower because of all its safety checks. On the other side, you have UDP, informal, no guarantees, but lightning fast. And here's the real takeaway. The magic of the modern internet isn't about one of these being better. It's about applications being smart enough to choose the right tool for the right job.
Okay, so we have two different messengers, TCP and UDP, and they're delivering mail to all these different mailboxes, or ports. But how does your computer know which mailbox belongs to which service? How does it know where to send a web request versus where to send a video stream? Well, that's where a standardized directory comes in. This right here is a small sample of what are called well-known ports. Think of it as a universal public address book for internet services. Every single browser on the planet knows that if it wants to load a secure web page, it needs to knock on the server's door at port 443 using the reliable TCP protocol. And every computer knows that to get its network settings, it should shout a request over to ports 67 and 68 using speedy UDP.
And, this isn't just some casual agreement between tech companies. This whole system is officially managed by a global organization called the Internet Assigned Numbers Authority, or IANA. They're the ones who make sure that port 443 means secure web traffic in Tokyo, Toronto, and anywhere else in the world. They create the universal standard that makes the global internet actually work.
So, at the end of the day, what should you take away from all this? It's not just how TCP and UDP work, but a really interesting question about the future. Right now, our world demands both. We want flawless, secure data for things like banking, but we also demand lightning-fast, real-time streaming for our entertainment. As those demands get even more intense, will the internet of the future keep relying on these two specialists, or will a new protocol emerge to give us the best of both worlds, something that's both fast and reliable? The answer's already taking shape, and it's going to define the next generation of how we connect.